Hello everyone, my name is Junil Kim and today I'm going to tell you about a paper and the title is Toward Optimal Mobility Aware VM Placement and Routing in Space Air-Ground Integrated Networks. There's a issues here. Internet-based services are offered by airlines today, like video streaming or web browsing. And additional operational services need to communicate to the ground, like monitoring data for flight status. So the conditions are services above here are hosted by virtual machine instances, which is located in data centers. Uh, and data centers are distributed in the ground network. Each type of service has different quality of service requirements, like delay. So, and here is the and here is space air ground integrated network. The airplane has two air to ground link alternatives to communicate to VMs in data centers. First alternative is satellite links. It provides network bandwidth globally to the flying airplanes. And satellites relay the received traffic from the airplanes toward their gateways. And second alternative is direct air-to-ground links. A direct air-to-ground node can establish a direct connection to the airplane whenever the distance allows the communication. It has higher link capacity, lower delay, and less cost than satellite connections. So it seems to that direct air-to-ground links performs better than satellite links. Here's a figure of space-air ground integrity network. Let me explain this. First, here's time slot t plus 1, t plus 2. So airplane goes t plus 1, t plus 2. And here are ground network. This is ground node, and this is direct air to ground node, and this is data center. And this is satellite gateway. And as you see, this is satellite node. The red line ground link links the ground nodes. It in short, ground interconnected. And you can see a green line, a direct air to ground link. So it connects airplane and DA2G node. And lastly, the blue dotted line, you can see the satellite link. So it links satellite gateway, satellite, and airplane. So here, satellites relay the received traffic from the airplanes toward their gateways through this line. And direct air-to-ground links connected through this line. This was the figure. So motivation of this paper is in case of overloaded direct air-to-ground connections, satellite connections may have to be used as alternatives. Again, in case of overloaded direct air-to-ground connections. Here's our considerations. So we need to replace virtual VMs on data centers. But there's a considerations. First is the available data center resources and their costs. In short, we have to consider compatibility. Second, the routing to the satellite gateway to guarantee the quality of service requirements. There are 4 questions should be addressed. First is, how many virtual machines of each service type have to be placed on each data center for each time slot? Second is, considering bandwidth and delay requirements, which paths should be used for airplane to virtual machine communications? Third is a virtual machine migration necessary? If yes, from which data center to which? And last, how to jointly reply to the aforementioned questions in a cost-efficient manner. So, we have to consider the mobility of airplanes, different locations at different time slots, and also the heterogeneity of the satellite SAGIN architecture. In this paper, a mathematical formulation was proposed to determine the optimal virtual machine placement, routing, and required virtual machine migrations at each time slot. So the name is Mobility Aware Joint Service Placement and Routing, in short MA-JSPR. In reference of this paper, we can find some formulation. First formulation is this. This is objective function for MA-JSPR. This term, costs under K per migration. This term is defined as the migration cost for service type K, and MK, NJK, YUV, these are weights and these are costs. So the total sum of costs, and we have to find the minimum value. And the next formulation is this. This formulation is to compute the number of migrations of service type K at the time slot T. So through these formulations, we can find the optimal replacements and routing. These are features of MA-JSPR. This solution considered costs. First is end-to-end routing cost from the airplane to the data center. Second is virtual machine deployment costs. And third is virtual machine migration cost between data centers when required. These costs are considered in once. And the feature and contribution of this solution is this solution. This formulation is based on the known future positions of airplanes, and this is an approach as an integer linear program, and objective of this formulation is to minimize the total incurred long-term cost. Evaluation. So evaluation of the formulation is shown as the graph. X index is sigma values and Y index is normalized average total cost. Compared to other formulation like S-JSPR, MA-JSPR shows a low average total cost, as you see here. Uh, TL means long term, long time. Well, long time. And TS means short time. Short time travel and long time travel. As you see, in TL, MHS M compared to S-JSPR, MA-JSPR has average total, low average total cost. And also in short time travel, MA-JSPR always lower than average total cost of MA-JSPR. And also in this paper, they demonstrated their optimal solutions. In realistic European-based, sorry. In realistic European-based satellite air-ground interconnected network. In short, they simulated a real European airlines. 3 airlines are flying over Europe. The optimal routing, virtual machine placement, and migration decisions at each time slot are depicted on the map as you see here. Scenarios. Here's a scenarios. There's some choices. First is number of flights over time flights. 1 flight, 2 flights, 3 flights, 3 flights. And second is number and location of data centers. Here is default, and dense data centers and high virtual machine costs. And you can also select cost values, in particular virtual machine deployment and migration cost. In short, these are configuration of scenarios. And output. The picture here is the output of the demonstrator. The optimal solution for routing, virtual machine placement, and migration decisions are visualized on. Oh, sorry, there's a typo here. It's on the GUI, as you see here. So you can see in this graph, flight 1, flight 2, flight 3, and by varying time slots, end-to-end delay is plotted like this graph. And compared to S-JSPR, as you see, by varying time slots, the total cost of MA-JSPR is lower than S-JSPR in all time slots, as you see. And total time cost is in dollars. So, conclusion. Contribution of this paper is the solution proposed in this paper can help airline companies to try out and evaluate different network resource management strategies for their network services through their formulation. And the approach can also be applied to other scenarios where networks change dynamically, like trains, ships, or self-driving cars. It's the end of the so thank you for listening.